into the meeting, but I mean, you'll do a better job explaining what you're about to talk about, so I'll turn it over to you.
Okay, sounds great. Let me try to share my screen. Uh, it's always tricky to do both slides and Zoom together. Uh, Continue to share. Okay, so can people see my slides?
Yeah, you
How
go.
about video? Are people able to see the video playing?
Yep.
Okay, perfect. So let me go back to the beginning. So it's my great pleasure to speak to you guys, the San Diego Astronomy Association. So I'm CK Chan. I'm an astronomer at the University of Arizona. So although my title is astronomer, I actually don't really know how to take astrophotography because I start as a theorist. So I like to study equations, general relativity, and do supercomputer simulations. But in the last 5 or 6 years, I've been involved in the Event Horizon Telescope that we combine many radio telescopes all around the world to image black hole. So I start to do data processing and all of that, and that is the thing I'm going to show you guys today. So by the way, please feel free to interrupt. And if you have questions, just stop me. I have way more slides than I can go through. So if people interrupt me, I will just spend more time on the slides that people find interesting. Otherwise, I will just skip some of them. Okay, so let's get started. So the thing I usually want to show people at the beginning is this movie here. So this is the Milky Way. In Tucson, we have gray sky. So usually during the summer, when you look up the sky, you can see something like that. And I hope San Diego can also see something like this. But if you look at this image, you can see a lot of dust in the galactic plane blocking the central area. So in order to observe the supermassive black hole at the center of the Milky Way, we need to go to a different wavelength. And we are now switching to radio. Okay, so in radio, you can see the dust all become transparent. They no longer block the light. And now if we just keep zooming into the center of the Milky Way, then you can see this very interesting filament structure that we don't really know what they are. And if you zoom in more, you see this structure that people call the mini spiral, but they are just molecular cloud moving around. And at the middle, there is this point here that if we keep zooming in, this is not just a point source, this is not a star. And because of the central darkness here, we actually conclude that this is a supermassive black hole at the center of the Milky Way that we call Sagittarius A star. This is a 4 million solar mass black hole, and a lot of work for the Event Horizon Telescope is about making image like this and also do measurement of this so that we can compare that with the theoretical predictions we have in order to learn something around black holes. So maybe just up to this point, do people have any quick questions?
I have one quick one.
Yep, sure.
I've heard the term interstellar dust a million times. What is it actually made of? Like, what is it?
That is a great question. There are just so many different molecules. All of them can become as dust as long as they block light. So I don't think there is a single very good answer. But whatever thing that is blocking, the optical light, we consider them as dust. So.
Okay, but it is solid. It's not like a gas or something.
Right? They are usually not gas. Yeah.
Okay. Cool.
Yep. Very good question. And this is the group at the U of A who contribute to this project. The Event Horizon Telescope is an international collaboration. So we actually have more than 300 members all around the world. And these people you see in this picture are from the University of Arizona. Right now our group becomes smaller, but we still have a few people working on this project. So there are many interesting topics I will go through. Again, I wouldn't be able to go through everything, so I will just skip some of them. So I think the first thing I want to bring up is really talk a little bit about black holes themselves. So let's zoom back out and do some physics. So all of you like astronomy, so I'm sure you saw your image like that the astronauts are in an International Space Station, and then you can see there's no gravity in the International Space Station. But for me, this is actually a very puzzling picture when I was young, because we know that there's a moon next to the Earth, and the moon is pulled by the Earth's gravity. The International Space Station is much closer to the Earth, and it's also pulled by gravity. So why in an image like that there's no gravity there? Do people have any thought, or anyone want to answer this?
Because it's always falling?
Very good. So this is actually what we call microgravity. It's not because there's no gravity. It's because the International Space Station itself is falling together with everything in it. So I have a cartoon here showing you this concept that if you throw something up, of course it will come down to Earth because of gravity. But if you throw something harder, farther away, it will take longer time to come down. But if you put a very large tangential velocity, when this thing tries to fall down, it actually never hit the ground. It will go around the Earth when it falls down. So that is what we call in the orbit. And this is actually exactly how many of the things we including spacecraft, International Space Station, everything on Earth that feel the gravity that work. So if we take this idea a little bit and do the following thought experiment. If we set up a elevator or this space station, we have a person, we have an apple in this space station. And if everything is falling together, inside the space station, you actually cannot sense gravity, right? So this is the microgravity we just mentioned, or why people say there's no gravity in the International Space Station. But if you do this thought experiment, the setup I just explained, there's no difference between that setup compared to a box very far in the deep space without any heavy mass around it. Right? Everything is free-flowing. So free fall is actually equivalent to there's no gravity. All right, so this is my superhero meme that if you remember Dr. Strange, Loki got very angry because he fell for 30 minutes. But Loki is an alien, right? So falling for 30 minutes is just like space travel. So he shouldn't get mad in that. But anyways, so now if we flip this thought experiment, we put this room we have on the surface of the Earth, okay? Now the gravity actually pull you down. So you, the apple, they're all at the bottom of this room. So now you want to compare this to the thought experiment we have. And this is equivalent to having a room, a spacecraft, accelerating in deep space. Okay? So right now this is just talking, this is just an idea. But the amazing thing that Einstein did 100 years ago was to say, hey, maybe this is not just analogy, but instead maybe the fundamental physics behind this are actually equivalent. So by doing so, he was able to write down the Einstein's field equation, and then the concept become, if there's no heavy object in space, the space-time itself is flat. So when you have particle, photon, they will just move in straight line in space. But now you put a heavy object somewhere, it bends the space-time around it. So now particle, photons, when they try to move in the strictest path possible in this curved space-time, they end up appear to be curved in 3 dimensions. Okay, so this is what we call gravity. And in fact, when you go to so extreme that it's not just particle that will get bent by gravity, instead, even photon will bend around it. And we can have region in space that this curve is so much that you will bend the space-time so that all the photon will fall into this region that we call a black hole. Okay, so this is the Einstein field equation that I just mentioned. I wouldn't go through it, but this is just a statement about the space-time curvature is equivalent to the matter density. And John Wheeler actually have a very nice way to say this, that space-time tell matter how to curve, how to move, and matter tell space-time how to curve. All right. And when Einstein wrote down that equation, he didn't think we can just solve it exactly because the equation is very nonlinear, very complicated. But shortly after the paper was published, actually Schwarzschild, who is this gentleman on the left, he was able to solve the exact solution for the Einstein equation. And based on this exact solution, we are already predicting there can be very strange object in space, that space-time is curved so much that photon cannot escape. Okay, and 50 years later, another gentleman, Roy Kerr on the right, that he add angular momentum to this solution, and it allows this black hole, these objects to spin. And today, when we study black hole, we still use the solution that Kerr derived. Right. So this is just a quick summary here. So when you have a black hole, it's fully described by the mass and angular momentum and the charge. But for astrophysics, we don't really care about the charge. So any black hole, they're only defined by two parameters, the mass and the angular momentum. And I think I can probably skip some of them, but hopefully this is a very quick overview of black hole. And I think the beauty here is black hole, this concept was actually predicted theoretically before we had any observation evidence. And it is this theoretical prediction that motivate astronomers who build telescope and form this large collaboration to image them. Okay. Any question up to this point? Okay, I can keep going. Okay. So we can set up the thought experiment that imagine you have a black hole and you shine a flashlight to the black hole. Because the gravity is so strong, or the space-time is bent so much, some of these photons will actually go around the black hole and come back to you. So even without any calculation, just by thinking, you can already tell a black hole when you shine a flashlight and look at it, it actually will look like a ring. All right, so this is very simple argument. And when we start to use, for example, the Hubble Space Telescope, look at all the galaxies around the world, we can tell that at the center of these galaxies, there are engine that can outshine the whole galaxy. Right? So this active galactic nuclear that we know. And if you write down the energy equation, then you find out that really not much process in astronomy that can create so much energy. So the only conclusion we have, even without resolving the black hole, is that we think they are supermassive black hole and almost all galaxy. And some of them, when there are enough gas falling onto them, they become so bright to outshine the galaxy and become AGNs. Okay? And if you think about this process, the black hole itself is black, so we cannot see them directly. When we try to observe them, it really is the matter that fall to the black hole that we are able to observe. So this is what we call accretion flow. And black hole, they are able to convert the energy in accretion flow to light much more efficient than even nuclear fusion. Okay, so black hole, they are, on one hand, they are the darkest thing in the universe, but on the other hand, they're actually the most powerful engine in the universe that can convert energy from the informed matter to emission. Okay, now for a theorist like me, just having the picture is not enough. We also want to study what happened around them. So we turn to supercomputer. So what I have here is something called general relativism little hydrodynamic simulation. It's very difficult to say, but what it really means is we set up this computational domain and then we put plasma around the black hole. But this plasma, they are not just gas and fluid, and in addition, we actually allow this fluid to interact with magnetic field. And when that happens, if you just put a very weak magnetic field in this plasma around the black hole, the state actually become unstable and you form turbulence. And you have this turbulence that is mixing the fluid and then they are able to bring the plasma down to the black hole. And along the spinning axis of the black hole, there are also outflow that come out. These are the jets. So nowadays, with this simulation, we can derive from first principle. We just write down the equation and we have this simulation very well model reality. So I think this is one of the very important advancement in the last 10 years. Okay. Now, just having the plasma simulation is not enough, because they give you the plasma state, but they doesn't tell you how the black hole look like. So in addition to the plasma simulation, we also develop this technique called general relativistic ray tracing. Now, for people who love video game, ray tracing is a term you already know. The idea is you set up your virtual screen, and for each pixel, you follow the geodesic. You follow how the photon will hit that pixel backward. And when you integrate this backward, you go back to the plasma that is emitting light. And along each of these light ray, you calculate how many photons got emitted from the plasma and how many photons got absorbed. So by doing calculations like this, you can actually predict how a black hole will look like. And this is a typical image of these simulations. So this yellowish ring here, this is exactly the ring I told you earlier when you shine a flashlight to a black hole. This is the region when the photons go around the black hole multiple times, and when they come to you, you see this very distinguished feature called a photon ring. But in addition to photon ring, you also see this purple pinkish emission. That is the body of the accretion fold. So these are the plasma falling to the black hole. But along the spinning axis, you can also see this funnel region that is pushing magnetic field and plasma out. So this is people call funnel, and if they are bright enough, we call them jet. And this is actually a movie. So let me play this. And while we are playing this movie, do people have any questions? Now, so if not, then one nice thing about doing simulation is you can control the camera. So what you just saw was we spin the camera location of this simulation, and you see the black hole, the jet is pointing into you and then come back out. And you can also see the location of this photon ring actually got shift when you change the camera location. That is an effect of general relativity. It's because the black hole itself is spinning, so it's dragging all the space-time around it, and that offset this photon ring. Okay, so unfortunately, in reality, we cannot just change the camera location to see this effect. So because of that, measuring black hole spin from black hole image is actually a very challenging task. Okay. Oh, so there is a question in the chat. Why is accretion so efficient? That is a great question. So the accretion process is mainly just friction and turbulence. The idea you can think about is when this accretion fold, this plasma very far away, they have a lot of gravitational potential energy. And when they fall to the black hole, that difference is huge. So when they are very, very close to the black hole, most of that gravitational energy is already released to become kinetic energy. And all the plasma near the black hole, they move at speed of light. Okay? But if there's no magnetic field, no turbulence, this plasma will just orbit around the black hole forever. They wouldn't fall into it. So what allow us to turn the accretion energy, this gravitational energy to emission is actually turbulence. Because this plasma interact with magnetic field and the configuration is unstable, they generate turbulence. So it's just the same turbulence that you feel when you travel in airplane. And the turbulence makes this plasma around black hole, and they turn all of the kinetic energy, which is close to speed of light, into thermal energy, into heat. So for the models that we are seeing, this plasma near the black hole, the temperature is 10 to the 10 Kelvin. These are extremely hot, and they emit not just radio wave, they also emit X-ray. So it really is the turbulent mixing that allow us to convert gravitational energy to light. Okay, there's another question, what determined the rotation axis? There's another very good question. So there are actually two sense of rotations in this kind of study. One is the black hole spin, the black hole itself spin, and that axis, depending on it depends on the formation history of the black hole itself. So we can't really control that. But there's also another sense of rotation, which is the plasma. The plasma themselves carry some angular momentum when they fall to the black hole. So this is just the environment that the interstellar media provide, and again, it's something else that we cannot control. But all these simulations I show you here, to simplify the calculation, we assume the angular momentum of the plasma is the same as the black hole spin. We assume the spin axis align. And that is the reason you see this very simple accretion picture. But there are also people who do calculation to allow these two axes to misalign. And in that case, the simulation becomes much more complicated, but also more interesting. You actually can see the plasma from far away. They form a bigger accretion disk. But when this bigger accretion disk get close to the black hole, because the black hole spin doesn't align, so you form another mini disk that will precess around the black hole. So there's a lot of very interesting physics from this. This is a great question. Okay, so we watched this movie for long enough, so let me go to the next slide. So up to this point, I just show you theory simulations. So let's talk a little bit about observations. So you all of you know about taking picture in astronomy. So there is a technique we call adaptive optics that allow us to correct for the atmosphere that that really messed up your astrophotography. So using adaptive optics, we are able to correct for the atmosphere distortion and have very high resolution of these stars near the center of the Milky Way. Okay, and by observing this star, we actually see they go around a region that there's nothing. Okay, so we are talking about optical observation here. So by observations like this, we can already tell there must be a very, very heavy object at the center of the Milky Way. But in optical, we just don't see it. Okay, and the observation I just mentioned actually led to the Nobel Prize a few years ago. And because by just checking the position of these stars, you can already estimate how heavy this central object is. And the estimation gives you 4 million solar mass. And because the region is so small, so the only theoretical explanation is it must be a black hole. So we know that it's a black hole at the center of the Milky Way before we were able to image it. Okay. Now, the reason it's so difficult to image, on one hand, is because in optical we can't really see it, but on the other hand, it's because it's extremely tiny. So in order to resolve this black hole, it's the same as resolving a donut on the surface of the moon. Okay, or the other way to say it is you want to resolve just a small piece of sand or salt on the east coast from the west coast. Okay, so it's very, very tiny. So in order to resolve the black hole, we don't use a single telescope to do it. And in fact, there's no single telescope on Earth that can have such a high resolution. So the technique we use to do this image is called very long baseline interferometry. The idea is we are taking multiple radio telescopes around the world. For a single radio telescope is very different from your standard CCD astrophotography. A single radio telescope is just a single pixel antenna. It cannot form an image. So what we do is we point this radio telescope to a region on the sky. So let's say this dotted line here is the sensitive region for the sky. And imagine you have a sub-feature in this region that is sending radio wave to your radio telescope. Now, instead of just capturing the total intensity, we put equipment in this telescope to record the radio waveform. So we have the voltage going up and down, positive and negative, and we keep track of the phase information of your radio wave. And now if there's another feature in this region that's also sending radio wave to you, and from this cartoon you can already tell they actually arrive to your telescope at a different time. There is a delay. So when we are So by doing very high time resolution recording of this wavefront, we are able to tell from this signal that there are sub-feature on the sky. Okay, so this is the whole idea behind very long baseline interferometry. We keep track of the phase information about of the radio wave, and we use that to reconstruct the black hole image. Now, if you only have 2 telescopes and you do interferometry, you cannot really reconstruct a 2D image. All you can do is to reconstruct the distribution of light in a one-dimensional line. So to do image reconstruction, we need multiple telescopes. And this is the Event Horizon Telescope Array in 2012. And we keep adding new telescopes to it. So in 2018, we have a few new telescopes. And nowadays, we even have telescope from South Korea and some other places. And we're also adding a new telescope in South Africa, for example. So we keep expanding the number of telescopes, but we also upgrade the instrument. Okay. So this, because I'm from Arizona, so for advertisement, this is our sub-millimeter telescope in Arizona on Mount Graham, and this is the Kipit telescope. Kipit is only 1 hour drive from Tucson. So if any of you visit Tucson, it's very easy to get to Kipit and see these telescopes. Some of our faculty also work at the South Pole Telescope. So we send students to the South Pole to install instrumentation in the South Pole Telescope to make the EHT work. So if any of you have your children who are also interested in astronomy, come to Arizona, and they may be able to also take a field trip to the South Pole. All right. This is a time lapse that I took during one of the EHT observation, and because this is a radio telescope, they even work during daylight. And with our new telescope in South Korea, the EHT now can almost do 24 hours observation. So as the Earth spins, we just bring different telescope online to do continual observation. In reality, we don't really do that, but it's more about operation limitation instead of the instrumentation limitation. Any questions up to this point? Okay, I see something in the chat. Let me take a look. Do all the telescope observe in a single frequency, or is it a mix of frequency? That is a great question. So in order for very long baseline interferometry to work, we need a single frequency. So for the 2017 observation, everything was observed in 230 gigahertz or 1.3 millimeter wavelength. So that is the standard frequency wavelength that the EHT use. But I may have a figure later that if we are able to observe in higher frequency, it actually increase the resolution. So we also upgrade our instrumentation to observe at 345 gigahertz, but not all the telescopes have that yet. Okay, there's another question of how do you share time on the scopes. There's another great question. So there are 2 sets of instruments we use to keep time. One is just GPS, because we need to synchronize the clock at the different telescope, and we use the GPS time. But for each telescope, we also have a atomic clock local to the telescope that gives us the oscillation. So the atomic clock gives us the timestamp of our observation, but we also use GPS to synchronize all the telescopes. What is the tolerance for time synchronization? Okay, so that is a technical question that I don't have an answer on top of my head. So I will say GPS type error is good enough, partly because we actually don't care about the absolute time delay, right? Because the absolute time delay gives you an absolute phase in the system, and that is something we don't really care. We care about relative phase. So, and in order to get this relative phase, we can also do calibration. I will have a slide later. So many of these time error, we can actually correct them after observation. So that allows us to even have bigger tolerance on this. But I don't have a very good number on top of my head. Okay, so let's go to the next slides. Okay, so because we are recording the radio waveform, we want to resolve this 230 gigahertz signal. So the data volume is very big. There are also some technical details here that we actually down convert the sky signal to lower frequency to the frequency that electronic can work. But despite of those technical details, the volume of the data is at petabyte scale. Okay, so what you see here was shortly after one of our observation. These are all hard disk that you are seeing, and this is 4 petabyte of data from the 2 Arizona telescope. And we have more telescope than just the 2 in Arizona. So the data volume for the whole project is quite big. It's about 20 petabyte scale. Okay, and because the data volume is so big, we can't really just transfer the data through the internet. So we need to ship them to our data center. And what you see here is people pack up the hard disk, use FATDA to ship them around. Okay, so I believe the EHT gave a talk to you guys in 2019, right? So that was probably the result for the M87 black hole. So that was the first image of the black hole. But the second image, the black hole at the center of our own Milky Way, that actually came out in 2022. The reason that it took us another few years to do the data processing, the main reason is the black hole at the center of Milky Way is about 1,000 times smaller than the M87 galaxy black hole. And because of that, everything, when you try to image it, everything moves about 1,000 times faster. So this is a good simulation to illustrate that. This simulation you're seeing is actually moving, but it's moving at M87 time scale. And when the M87 black hole is moving very, very slowly, the black hole at the center of Milky Way is moving at this speed. Okay? So the time scale is 1,000 times quicker, faster. So when we are taking data of the galactic center black hole, the black hole image itself is changing. So because of this variability, the image reconstruction requirement is just much harder. It's very difficult to do that image reconstruction. So one way you can think about it is when you take a picture of M87, it's like this cute puppy just staying there for you to take a picture. But for Sgr, it's chasing its tail, it's moving, so it's very difficult to take a picture. And in addition to that, because Sgr star is at the center of the Milky Way, so when we observe it, there's so much interstellar media in the middle. Now, they don't really absorb radio wave, unlike the dust we mentioned earlier, but they still scatter light. Right? So they are a little bit like this foggy screen on the right that actually affect your image. So all of these effects make the galactic center black hole much harder to image. And because of this, when we do image reconstruction of this radio waveform data, there are millions of images, all of them are consistent with the data. Okay, so in this movie you're seeing here, all of these images, they're consistent with our data. So all of them are actually valid reconstruction of the black hole image. Okay, now in order to really make sure that we are seeing a black hole, the Event Horizon Telescope, in addition to image reconstruction algorithm, we also develop machine learning AI methods that automatically classify our millions of image reconstruction. Okay, and when we do this classification, you can tell most of the image, they actually look like a photon ray. Okay, there are only very few images that is showing something different. So using this gives us some sense of a statistic statement about the black hole image, and we are pretty confident that this is actually a black hole with a central darkness, which is a projection of the event horizon. So I know that is a lot of information. Do people have more questions at this point? Okay, if not, we can keep going. Now, the image at the beginning of my slides, you can see these additional lines on the image. So these are not real in some sense that we don't have such a high resolution to resolve magnetic field around the black hole, but they are just representation of polarization. So people who drive on highway, you need a polarized sunglass to reduce the reflection. So it turns out that this radiation around black hole, because there's magnetic field, they are also polarized. And the EHT, by recording the radio waveform, we have full information about this polarization. Okay, so when we do this image reconstruction, we can also reconstruct the polarization information, which allow us to estimate the shape of magnetic fields and magnetic strings around black hole. So this is what our result is about. So in addition to just the black hole image, we also have information about polarization in magnetic fields. Okay, so let me just, in the last 10 or 20 minutes, I can show you a few more simulations. We use these simulations to compare with the observation in order to understand what the black hole is about. So on the screen right now, this is one of our black hole simulation. You see this photon ring, very standard image. But because we don't really know the parameter of the plasma around the black hole, so there is some value that we can change in our study. Okay, so this is one of our black hole simulations. But because we don't know the parameter, so in this simulation effort, we create a library that we change the inclination of the black hole. So it's where the spinning direction is pointing to. So you can look at the black hole face on or edge on. But we don't know the black hole spin itself, so there is another parameter that we can change. Now, in addition to this parameter, we also don't really know the plasma temperature. We don't know how hot the plasma is. So that is another parameter that we adjust. And finally, there are different magnetic configuration around black hole. So that is the final parameter that we also change. So what you see here is a subset of our simulation library. So in order to understand the physical environment of the black hole, we run so many supercomputer simulation, create a library like this, and by comparing all of this black hole movie to what we observe, we can start ruling out parameter that doesn't make sense and learn something about black hole. So the first thing we can use is to use the black hole image size to rule out some of the models. And it turns out it wouldn't rule out that many models. You only rule out a few. The reason is when we build this model, we already have the estimate of the black hole mass. But if you take the shape into account, the shape of the black hole image into account, you rule out more information. If you bring in multi-wavelength information, you rule out more. And at the end of the day, in this very big simulation library, there are only two models that are consistent with our observation. So this is our best model of the supermassive black hole at the center of the Milky Way. And by looking at the details of this model, we can say a few things. So one thing is the plasma around this black hole, there are two temperatures. So this is a little bit technical, but what you can imagine is the plasma around the black hole is very dilute. So the electrons, when they an ion, when they move around the black hole, they don't really collide with each other. So that allows the electrons and ion to have different temperature. So the observation demand that we have these two temperature plasma to explain the observation. Another thing is we also know this black hole is magnetically dominant. The magnetic field is so strong that they can stop the accretion flow. If you compare the galactic center black hole with M87, for example, our black hole is actually very dim. So one explanation is because the magnetic field is strong enough to stop the plasma falling into it. So there are only very few plasma that give us the emission. That's the reason it's so dim. Let's see. Yeah, so these are the main physics that we learn about the black hole. Now, when we have this information, we can also ask a deeper question. At the beginning, I told you that black hole, they will first predict theoretically, right, before we observe them. So after we do all of this observation and model comparison, you can start to ask, is Einstein's prediction, is that really correct? After we can finally observe black hole, does the observation contradict Einstein's theory? So that is something we do in the Event Horizon Telescope. In addition to this standard black hole simulation, we also simulate crazy things like wormhole, boson star, this very interesting theory. But looking at the prediction, you can already tell these different object, they will show up differently than a black hole. For example, wormhole is the lower right image. It does look like the black hole image, but if you consider all the mass, all of those constraints, they are slightly smaller than black hole. And lower left, we have something called boson star. This is also some theoretical prediction. If you just have boson and then they can support this very heavy gravity, instead of a black hole, you could have a boson star. But for boson star, you don't really have the central darkness. So by comparing this prediction with observation, again, we can rule out many of these possibilities. And in addition to just looking at the morphology, how things roughly look like, we can also go to the black hole image and then do accurate measurement of the size of the thickness of the photon ring. And by comparing this measurement with detailed simulation, again, we can conclude that the black hole observation is actually consistent with Einstein's prediction. And because these measurements are done as so close to the black hole, they are in a very, very strong gravitational regime. So the test of general relativity itself is about 1,000 times better than any other test possible. So Einstein's general theory of relativity is also tested in the solar system. But that is what we call weak field test, because the gravity in the solar system is relatively weak. But when we image the black hole, because the test is near the black hole in strong gravity, so even though our error bar is bigger than the solar system test, but because gravity is so strong there, the overall test of gravity is still much better than the solar system test. So I think this is, I would say this is one of our strongest science output of this whole project. Now I also want to say a little bit about the future. The EHT, we keep upgrading our instruments, so the image I just showed you is not the end of the story. Instead, we keep asking, can we make our measurement more precise so we can push our test of gravity even better? So something that we did earlier this year in spring 2026 was we tried to capture a movie of a black hole. Usually, the EHT observes about a week per year. So because we don't own any of these telescopes, right? So we need to apply to time and we need to coordinate all of these telescopes around the world. Before 2026, we can only afford observing for a single week per year. But in 2026, we managed to observe for about 2 months. So the observation is 2 days per week and then continue for 2 months. And now we have 18 days of observation. So our hope is by constructing this image on every day, at the end of the day, we will have 18 frame movie of the black hole. Now, however, when we do this observation, you can't really control what the black hole is doing, right? So if we are lucky, then we may be able to see the black hole is moving. That will be wonderful. But even if the black hole is not moving when we do the observation, we can still combine this multi-day data set, average them, and have a better measurement of the photon ring diameter and the width. So that will give us better constraint on the gravity. So if the black hole moves, we will have better understanding of the plasma around the black hole. If the black hole doesn't move, then we will have better measurement of gravity. So I think we can only win in this situation. And this is some of the analysis tool that we are developing. Assuming this black hole image actually moves, we now have image reconstruction algorithm that can reconstruct movie and do interpolation for us between frames. And this technique also allows us to map out the velocity of how the plasma is moving. And actually, I think there are just 2 Nature papers just published, I think maybe yesterday, that talk about this algorithm. So I encourage you, many of you can just look up the paper. All right, so making movie is something we are able to do now. But in the EHT, we also want to add more telescope, because the more telescope we have, we will have better signal to noise ratio, and that allow us to resolve the dimmer part of the image. Actually, in this image I'm showing you here, you can see the base of the jet. So this is the M87 Galaxy. It has a jet coming out. In the original image, we didn't have enough dynamical range to resolve the base of the jet. But by adding more telescope, we can you have a creditable reconstruction of the base of the jet, and that will explain. That will let us figure out the magnetic field configuration near the black hole and understand how black hole launched this very big jet. So this is very interesting science. But in order to do that, we need to add more telescope. So this is what the next generation Event Horizon Telescope program is about. This program is trying to bring more telescope to the array. So including a telescope in South Africa, a few more telescopes in the US. So if this works out, it will be very exciting. In addition to that, we are also working on a proposal. I think the proposal is almost done. That we want to put a space mission, put a satellite in space. Now earlier when I explained how the EHT work, we have these 2 telescopes on Earth nearby in my cartoon. Now you imagine you put one of those telescopes very far away in high orbit. If you do that, because you have a very long baseline, it actually gives you very high resolution information about black hole. So this is what we call the Black Hole Explorer that we are proposing to NASA. And if we get this, then this will be very amazing, because we can do very high accuracy measurement of this photon ring around black holes. Okay, so I think this is all the slides I have, and I also hit the hour. So thank you very much for your attending, and let's take some more questions. Any questions from people?
I have a question.
Okay. Yep.
What is the actual? So you say that each radio telescope is effectively like a single pixel, right? It's sort of pointing at a point source. So what is the data on all those hard drives? Is it just a waveform of a specific frequency? So it's like, is it just amplitude? Like what are you actually recording?
Yeah, so that is pretty much the amplitude. So the technical detail is 230 gigahertz is still the frequency is still too high for electronics. So we have the atomic clock local oscillator to down convert those to electronic frequency, and then we just record the voltage on that come out from the converter. So this is just positive and negative voltage that we are recording. And the actual amplitude, it turns out, is not that important. The most important information is in the phase. So what we do is we calibrate away the overall amplitude of this signal, and we just keep track of the positive and negative. We use only 2 bits of information to record this wave.
That's wild. And you're still filling. So like those, you say it was 4 petabytes or 40 petabytes? That was that picture.
4 petabytes.
4 petabytes of just 2-bit data?
Yep, 2 bits.
That's how, so is it for an extended period of time, or like why does it end up taking up so much space?
Yeah, so exactly. So this is your multi-day of scan. So that 4 petabyte of data was one observation campaign. So this is about 1 or 2 weeks, about 5-6 days of observations. Yeah.
That's cool. Do you guys get any, like, is there any noisy sources you have to account for, like satellites happen to be passing in between you and the, Sagittarius A star? Like, what sort of things do you have to clean up in that data?
Yes, that is another wonderful question. The biggest thing we face is just the atmosphere, because that distorts the radio waveform. But it turns out, so I think one nice thing about VLBI is because we record everything on hard disk, right? So you can use post-process to correct for that. So we use that technical, what we call fringe fitting. What that does is just rotating your phase and try to figure out what type of rotation will give you the maximum signal. And that is how we correct for the atmosphere. Yeah.
Cool.
And I guess another thing that people may not think of is because when we turn this radio data into useful information, we need to do cross correlation between two telescopes. So some crazy thing happen at one telescope. It actually doesn't affect the data because when you do the cross correlation, they will cancel out. So.
Yeah. You see it, you're like, well, that's definitely an outlier. That was something weird. Okay.
Yep, that's right.
So how do you turn that into a picture?
Yep, that is another very good question. So I just mentioned we use this cross correlation between the two telescopes to turn it into actually usable data. So after you do the cross correlation, you can prove it mathematically. The result is actually the Fourier transform of your image.
Okay.
Okay, so at the end of the day, we gather this voltage data at the telescope. They're actually not usable yet. So we cross correlate them, turn them into Fourier coefficient. So Fourier coefficient encode the information about image. And then when you have enough of them, then you pretty much do an inverse Fourier transform to get back the original image.
Wow.
There's one more question in the chat from Rich.
Okay, so let me try to stop. Yeah, so one annoying thing is I cannot see my mouse pointer, but okay, after I stop it works. You appear that radio waves come to these receivers at different times and perhaps through different paths. Is there not specific issue due to curved space-time? How we solve? Okay, so that is a great question. So we do see the curved space-time, but that happens very close to the black hole, right? So all of these curved space-time effects, they are already captured in this photon ring, in this ring-like structure. So that is the major curved space-time effect in the image. But when they come to the Earth, the effect of the atmosphere is way bigger than the gravitational effect on Earth. So. Any other questions?
Looks like we're good. And thank you for also answering questions throughout. I think that was super helpful and a super, super interesting talk. So we really, really appreciate your time.
Yeah,
thank you. No problem. So I know VLBI is not just your standard astronomy imaging. So it's getting technical. So I do think having Q&A along the way is useful.
Yeah, that was very cool to hear about. I certainly hadn't heard about that type of imaging before. So, yeah, amazing.
Yep.
Great.
Yeah, so it's a great pleasure talking to all of you. I hope that some of this is understandable and some of this is fun. So
yeah, that was.